Welcome to Learn Chemistry Together. This video is about an introduction to organic chemistry, the old divide. If you step back into early chemical history, science drew a very strict line between two types of matter, organic and inorganic. On the left, we have organic compounds. Historically, these were believed to come exclusively from living organisms, plants and animals. Think about things like the sugar powering plants, the proteins making up mucil and natural alcohols. Scientists once believed these molecules contained a special light spark that nature alone could create. On the right, you have inorganic compounds. These were derived purely from non-living sources, like earth minerals and atmospheric gases. Think of everyday table salt, pure water, or ammonia gas. The sparks that changed chemistry. In 1828, Friedrich Wöhler, a 28-year-old German chemist, were attempting to synthesize ammonium cyanide in his laboratory. Now, ammonium cyanide is an inorganic salt, a mineral compound you could make from inorganic salt starting materials. He took his solution, applied heat to evaporate it, and expected to get standard inorganic crystals. But when he analyzed what was sitting in his porcelain dish, he was stunned. It was not ammonium cyanide anymore. Heat had rearranged the atoms to create urine, a well-known organic compound found in animal urine. Whole family wrote to his mentor, John Jacob Berzelius, "I must tell you that I can make urine without needing a kidney, or indeed any animal at all." This single experiment, the Whole synthesis, proved that organic molecules don't require a mystical vital force. They are subject to the exact same laws of physics and chemistry as salt, water, or iron. Today we define organic chemistry not by where a compound comes from, but by what it's made of, carbon by chemistry. The blueprint of life. Once we realize organic chemistry is simply carbon chemistry, we began to see that carbon is the primary building block of life itself. Look at your raw body. If you strip away the water, almost everything left is an organic compound. For example, DNA, the double helix master blueprint storing all your genetic information. RNA, the messenger that carries instructions to build what your body needs. And proteins, the enzymes, structural beams, and work for driving your muscles, skin, enzymes, and immune system. Why carbon? Why is life built around this single element? Carbon is uniquely versatile. It has 4 valent electrons, allowing it to form stable covalent bonds with itself and other elements like hydrogen, oxygen, and nitrogen. It can form long chains, complex rings, and intricate 3D branches. Without this molecular flexibility, complex biological machines like DNA and proteins simply couldn't exist. Understanding organic chemistry didn't just explain life, it allowed us to build the modern world. Once chemists realized they could synthesize organic molecules, they stopped relying solely on nature and started creating custom materials. Today, 5 massive industries rely directly on synthetic organic compounds. Pharmaceuticals, from simple aspiring to life-saving antibiotics and targeted cancer therapies, almost all medicines are engineered organic molecules designed to fit key targets in our bodies. Pesticides and agriculture, modern crop protection use tailored organic compounds to safeguard global food supplies against pests and diseases. Paints and coatings, the resins, solvent, and binders that make paint stick, dry, and resist weather are all carefully formulated organic polymers. Adhesives, from everyday glues to super strong structural epoxies holding airplanes together, adhesive bonding is driven by polymer chemistry. And lastly, plastics and polymers, water boxels, synthetic textiles, medical tubing, electronics casing, plastics are synthetic chains of organic monomers that reshape human industry. That's all for an introduction to organic chemistry. Thank you for watching and please subscribe for more.